Hello, everyone. It's my great pleasure to introduce Dr. Peter Kairouz, who is a research scientist at Google, where he focuses on researching and building federated learning, differential privacy, and other privacy-preserving technologies. Before joining Google, he was a postdoctoral research fellow at Stanford University. He received his PhD in electrical and computer engineering from the University of Illinois at Urbana-Champaign. He is also the recipient of the 2012 Robert Padovani Scholarship from Qualcomm's Research Center, the 2015 ACM Sigmetric Best Paper Award, the 2015 Qualcomm Innovation Fellowship Finalist Award, and the 2016 Harold Olson Award for Excellence in Undergraduate Teaching from UIUC, and the 2021 ACM Conference on Computer Communication Security Best Paper Award. Thanks again, Peter, for accepting our invitation. The floor is yours.
All right, thanks a lot for this very nice introduction, and hi everyone. I'm very happy to be here, and today I wanted to talk a little bit about large models and foundation models within the broader picture of privacy principles and privacy technologies. So this is a bit of a new mix of topics, so I hope you will like it. And feel free to please interrupt at any point in time, ask me questions, and even after the talk, if you want to connect on Twitter or anywhere to continue the conversation, please do it. All right, so there's this beautiful vision of foundation models where you take large swaths of data. We're talking text, images, speech, structured data, 3D signals, sensor data, all kinds of data. And you build this one big, gigantic, massive model. We call it a foundation model because it's the foundation of many smaller models that are customized and adapted for specific tasks. For instance, if you want to do question answering, if you want to do some sort of information extraction, object recognition, instruction following, all those beautiful tasks. And we've seen over the past 4-ish years, the rise of these large, gigantic models, starting from BERT to GPT-3, CLIP, DALL-E, Lambda, ChatGPT, and there's a lot more. Now there's GPT-4, and there's every single company is racing to push one of these big models. If you want to read more about this vision, Stanford's HCI has this beautiful paper called On the Opportunities and Risks of Foundation Models. I strongly encourage you to actually take a look at it. Now, this is beautiful. This is actually really a pivotal moment in our community. So we should be fascinated by the potentials of it, but it also carries a lot of risks. And a lot of these risks are probably things that you've thought about, things like factuality and correctness. I'm sure you've all used ChatGPT or any of these big models from Bing AI to BART to others, and you've noticed that they make a lot of errors and they hallucinate. They're not correct all the time. There's also a lot of inequity and unfairness that the models have picked up from the training data or the algorithms themselves. They can be misused and abused, possibly by large entities or powerful entities. They can, for instance, create safety hazards to the environment. They come with security and privacy risks. And there's also the big question about copyrights and intellectual property. Are these models producing text that authors have written, or code that software engineers have written, or drawings that painters and artists have generated, music, so on and so forth? So tackling all these risks would take possibly a semester-long course, and this is not what I'm going to even attempt to do. In this talk, I'm going to mostly be focusing on the privacy risks and mitigations for these ML models. So that's going to be the focus of my talk, and I want to begin by demonstrating some of the issues that happen here. This is a not so recent, now 2-ish year old paper by my colleague and friends at Google, where they show that if you take GPT-2, and if you just take it and try to poke it, you can already extract a lot of sensitive information. We're talking about you can extract, if you prompt engineer it, things like an individual person's name and email, address, phone number, fax number, physical address. These are all redacted to make sure the person's privacy is protected. But you literally can remove and extract a lot of such information. Now, obviously, a lot of people would say, hey, look, GPT-2 was trained on web data, and this information is actually available on the web, but this information is not readily and easily available on the web. You have to really crawl and sift and look and put in a number of hours to find this information. These models are actually making it really easy sometimes for people to find this information. Now, obviously in ChatGPT and Bard and Bing AI, there are some guardrails to actually protect these models from spitting out such sensitive information, but still there is a lot of evidence of some research that shows that you can prompt engineer them and you can still extract a lot of sensitive information from them. And this is not specific to LLMs. This is also the case for the newer class of image generative models. These are the diffusion models, whether they're medium, small, or large models. And this is again from Nicholas Carlini and some of my colleagues at Google, where they show that you can really extract and generate a lot of images that were found in the training data set. And some of these images were not very common in the data set. Some of these images were less frequently kind of in the data set. And by cleverly designing inputs to the generative model, you could essentially recover and retrieve a lot of the training examples. This obviously presents a lot of questions on the privacy front, not necessarily showing a bulletproof example of a privacy violation, but it does raise some questions about what has this model memorized and overfitted to. But it also presents a lot of questions on the copyright front. For instance, you can see there's the Netflix logo there. And if the generative model here, this image generative model, starts producing something that looks a lot like the Netflix logo, you know, and some company is going to use some material like that in whatever advertisings they're running, there might be some copyright infringement happening here. So these are some of the questions that one has to keep in mind. All right, so the one thing that I wanted to say, and I wanted to be very clear, is that privacy is not a binary quantity. It's not either there or not there. And it's not even a scalar quantity. And that's even more fascinating. It's a multifaceted, multidimensional quantity. And over the past few decades, we've been really working with engineers, with philosophers, social scientists, UX, UI designers, so on and so forth, to try to understand what is privacy. What does it mean? What shape does it take in what context? And so we're only now converging on some principles that separate certain concerns that different parties have. And if you want to learn more about these principles, we've put out recently a paper called Federated Learning and Privacy. It was published in Communications of the ASEAN, and it's actually a very short, very non-technical paper that I invite you to look at it. But here's a quick summary of what is in that paper. We try to divide the space of privacy principles that are important and relevant into roughly 3 tiers. And these are principles for the users and for the platform itself, and then for the verifiers. And for the platform, we have 2 privacy principles there. So I'll try to go over these privacy principles one by one. And again, feel free to interrupt me if you have any questions or if you want to learn anything specific about anything that I say. So let's start with the first one, which is about transparency and user-centric control. So this is about really telling the user what data was used to train what models, and for what purpose it was used, what do these models do, what is their capability in some sense, and how it was processed. For instance, these foundation models, you keep hearing that they were trained on public web data. And you keep hearing that they were trained on a collection of social media data, on Wikipedia. There's this common crawl data set, C4, so on and so forth, if you've seen or toyed with these data sets. And these are all, kind of examples, training examples that you can find on the web if you scrape the web enough, and if you look enough, and if you search enough. But increasingly so, companies have been less and less transparent about these data sets. If you look at GPT-4 and you read their report, they don't tell you at all what the data set was. They cite the competitiveness of the landscape and avoid talking about neither the model architecture nor the data set. And other companies do the same. I'm not just pointing fingers to one entity here. So the issue here is that simply because some data is on the web does not mean that it's automatically always okay to train on it. For instance, take this example where I put some tweet on the web, And maybe a few weeks later, I discover that my tweet actually is inflammatory or something that I regret or I don't want to say, or I've revealed a lot of information that I didn't mean to reveal with the public. And so I could easily go and delete my tweet. But if somebody had scraped off the web and taken my tweet and used it to train a model, and somehow that model is overfitted to that training example, now the model essentially has memorized my tweet and could potentially spit it out if it's prompt engineered, or maybe sometimes even if it's not prompt engineered. And this could present a challenge because if you look at some of the European regulations, such as GDPR, they have a thing that's called the right to be forgotten, meaning that I could tell the company, hey, I want you to delete my data, whether it's my tweets, my text, my clicks, swipes, search, view history, so on and so forth. And they not only have to delete that data, they have to go and remove that data from any ML model that they have trained on that data. And that's why in a lot of companies, they have policies that they refresh these models that are used every 30 days to ensure that if somebody chose to delete their data, the data is removed from whatever models they're using in production. But now with the rise of these foundation models that are trained on web data, if I tell Twitter to remove my tweet, Twitter could go and remove my tweet from whatever ML models they've trained on Twitter data, because they know that relationship. I'm telling the platform itself to delete my tweet. But if some other entity, say OpenAI or any other company, had scraped off the web, how would they even know that I've told Twitter to delete my tweet? So this is going to really present a challenge for GDPR's right to be forgotten. And it's not going to be easy to give the user-centered controls and transparency that they very much desired. Lastly, on this principle, I want to emphasize that even though these models are actually trained on a lot of web data, and that's actually quite cool, they often are customized, adapted, and fine-tuned on sensitive data. These could be potentially emails, messages, watch histories, so on and so forth. And now we're not talking about web data anymore. Now we're talking about user data. And so this is where you need to be absolutely transparent about what you're doing, who has access to that information, and for what it is used. And so we need better communication with the users about how and why we're training these models, and what protections, if any, are we given to the users. And so this naturally takes us to the second privacy principle, which is really a principle about data minimization. So this is about only collecting the data that is absolutely specific for a computation. And it is about limiting access to the data at all stages. So not everybody at a company has access to everyone's data. You have to have strict limitations on that. And you have to be able to design pipelines that process the individual data as early as possible. So this is known as early aggregation. And then once you've processed the data to train a model, you need to quickly discard both the collected and processed data as soon as possible. And this is known as minimal retention. So these are really the core pinnacles of data minimization. And so on this front, I wanted to talk a little bit about this technology that is called federated learning that comes in two flavors. There is the cross-device federated learning, where you're trying to train a model across a large fleet of devices. Think of these devices as phones, tablets, computers, sensors, whatnot. So there's many millions of them, if not billions of them, and they each have a local data set of maybe tens, hundreds, or thousands of training examples. Not enough to train a big model, but collectively, if you put all the 100 million users' data together, you can train these large models. And so cross-device federated learning is a way to orchestrate this computation without sharing the data with the server or with the clients amongst each other. So the data resides on the user device and will always only be on the user device. It's never shared across the devices. It's never shared with the server. And this creates a beautiful vision where there could be data set heterogeneity, because my preferences is probably very different from each and every single one of your preferences. And it creates a lot of opportunity for load imbalances. I interact a lot with my phone. I text and chat and email. So I have a lot of training examples. Maybe one of you doesn't like to use their phone as much. They use their laptop more. So the phone has a lot less examples. So a lot of load imbalances. It creates beautiful opportunities for research. There is another setting of federated learning, which is known as cross-silo federated learning. And in this setting, you have institutions rather than essentially devices. So think of these as hospitals, think of them as banks, or even as schools or government entities, so on and so forth. Moving data across these large institutions is actually usually not okay due to strict regulations. For instance, there's HIPAA regulations. In the financial sector, there's a ton of regulations that protect clients and confidentiality and antitrust, so on and so forth. So it's not easy to actually move the data around from one hospital to the other or one bank to the other. Now, what's interesting about the setting is that rather than having millions or billions of clients or institutions, here we have maybe tens, hundreds, at most thousands. And every one of these entities has a lot more data. It has data for hundreds, thousands, or tens of thousands of clients, even more in certain cases. And they have more compute capabilities. They can have GPUs and TPUs and data centers. They can have sophisticated IT as well. But still, the data resides locally. And still, in most cases, it's not enough to train these large foundation models. So you still have to orchestrate somehow to combine the intelligence across all these organizations in order to train the model that you are after. If you want to learn a lot more about these two settings and their characteristics and properties, there is this now rather old paper called Advances in Open Problems in FL. I still invite you to look at it because it's still very relevant today. But what I wanted to emphasize for both settings of federated learning is that they encode by design the data minimization principle that we just talked about. They have minimized data exposure because we're not sharing data across users or with the server. They send only focused update because the model is actually trained on device, and you only send the model delta, that update, back to the server. So it's focused update, and then those updates across users are immediately aggregated, and everything else is discarded. You can only keep the final model. All the intermediate models are discarded. All the user updates that are sent back to the server are discarded. So these are anonymous, ephemeral updates. And then even the server itself would have a very limited release to the engineer that has requested the model that's being trained. Think of this engineer as possibly being, I don't know, Google's keyboard team at Google. And they have requested to train a next word prediction language model on Gboard data, for instance. And finally, the most important layer of data minimization is we only do at the end of the day, after we've A/B tested and verified the performance of the model, we only release a single model for deployment. And that is, again, another layer of minimizing data and reducing the threat of attacks. Now, what's also very beautiful in this is that data minimization could be strengthened. And this can be done via the use of some sort of secure multi-party computation and trusted execution environments. And I'll tell you about it in a bit. But before I do that, I wanted to present one classical algorithm that's very widely used in the setting of federated learning, and it's called federated averaging. So here what happens is that the cloud would send to the device the latest model, and this is shown in the purple box here. And on device, the model is actually trained using the local data. You do some number of SGD steps, and there's a lot of interesting, beautiful theory and empirical research here on what kind of optimization should we run on device for efficiency and for generalization and for data heterogeneity purposes. And I'll touch briefly on it in a bit. And then once you've trained that model on device, you send the delta, the model delta, back to the cloud. So a bunch of users in a cohort, think of them as maybe 10,000 users, would send back that model delta to the server, where the server aggregates these things. You simply do some weighted average. Basically, how many training examples each user had, I would give a weight proportional to that, to the update that I got from that user. And I just average things together in a weighted fashion. And I update the model, and I keep doing it again. So this is very easy. It's called federated averaging. And you can take it in many different directions. You can generalize it. So this is really here in this algorithm called federated optimization because it encodes a lot of things. So you have essentially the client optimizer, the optimization routine that's ran on the client device, that can be an arbitrary thing. You can think of, for instance, using some sort of momentum, atom, grad, all sorts of new and interesting optimizers. You can use adaptive optimizers, so on and so forth. But you can also generalize the step that's done also on the server. So you can have a server optimizer, and that too can take many different shapes, and it can have momentum included in it. So the two important things here that I'm highlighting on this slide is that you can have a client optimizer and a server optimizer, and those can generalize federated averaging in many different ways. You can create many different algorithms. And if you want to learn a bit more about this, there's this paper called Adaptive Federated Optimization, which really compares a number of different client and server optimization routines. Since then, a lot has happened. Our understanding has evolved. There's so many different flavors that give so many different guarantees for a variety of settings. So there's no one size fits all. And I just invite you to look at the literature that's constantly evolving. And that's really kind of all what I wanted to say, but they all live under this family of FedOpt, essentially, this federated optimization. All right, so back to what I was saying before, which is strengthening data minimization. And I was saying that we can use cryptography and we can use multi-party computation and trusted execution environments. And this is because if we use these technologies, we can prevent the server from actually accessing even the updates. And there's been a lot of research recently that shows that these updates that go from the client to the server can themselves include some sensitive information. You can try to invert them. You can try to do attribute inference on them. You can try to reconstruct training examples on device. So there's a lot of people that actually showed that, hey, you know, even if we are never sharing the data with the server, the update that the client is sending back to the server itself could have overfitted and memorized, and I could retrieve something sensitive from it about the user. So one way to actually tackle this question is to say we're going to use the old and tried security and cryptography primitives, and these are encoded in multi-party computation and trusted execution environments. So I'll give you an example. This is called secure aggregation, and I'll not do it justice, but I just want to overview it in one slide, which is basically a cryptographic primitive that allows the server to obtain the sum of high-dimensional vectors of client-held data. These are the model updates, essentially. But it ensures that the server can only learn the sum and nothing else whatsoever about the individual vectors themselves or model updates. So this is done using secret sharing. And there's a large literature on how we can implement secret sharing in an efficient way with a single server and how we can reduce the computational and communication costs. And if you want to learn more about this protocol, there's these two beautiful papers that I'm citing on this slide, but there's a lot more papers that look at primitives to design secure aggregation in the wild. So I also invite you to look into this literature. I'm mostly overviewing it in this slide. The one thing that I want you to actually keep in mind is that all these operations are done on finite groups and finite fields. So we have to be very careful because we're adding these vectors and we need to represent them in integers modulo the size of the group. And all the operations, the additions that we do are actually done on that group. So how we discretize and represent the model parameters in a finite group fashion is actually quite important, both for privacy, and we're going to talk about it with DP, but also for efficiency and accuracy. All right, so this naturally brings us to the third principle, which is about data anonymization. And data anonymization here is a term that we have used according to some of the regulations, so like GDPR and whatnot. And you may have seen people talk about anonymization differently, but we're mostly strictly abiding by how it's actually used in data privacy regulations. And so let me define it. It is about making sure that whatever is released at the end of the day, so the output of the computation, whether it's a statistic or a model that we're computing or a large model that we're computing, that statistic does not reveal anything unique about an individual. So aggregate statistics, including model parameters, when released to an engineer or even beyond, say they are deployed, should not vary significantly based on whether any particular user's data was included in the training or in the aggregation. And you may have guessed that the gold standard here is differential privacy. And so what differential privacy says is that if you try to perform a query or a computation, this query is, I'm training a large model, for instance. If you perform it on a data set D or an adjacent data set D prime, the output of these two results should not vary substantially. If the two outputs are very, very different, then an adversary who kind of has side information into what the output could look like could determine whether you've trained on data set D or D prime. And so differential privacy uses this information theoretic language. It uses what's commonly known as the infinity divergence or max divergence to say that the distributions of the output should be close in some sense. And this is what's given on this slide. And it uses two parameters to actually determine how close these two distributions should be to one another. There's one that's additive, and that's one that's multiplicative in the exponential. These are the delta and the epsilon. And the additive term delta should be cryptographically small. So you should think of it as 10 to the negative 6 or 10 to the negative 9. And the epsilon should be in the single digit regime, usually for this definition to give you some privacy protections. Now, what I have not touched on in this slide is what are these two adjacent data sets? I've actually intentionally did not talk about what's D versus D prime. I just said two adjacent data sets. And this actually is quite important, even though it's often left out. And what we really mean by D and D prime being neighboring data sets or adjacent data sets is that they differ by a unit of X training examples. And so this is important because this is going to dictate the scope of the privacy or the unit of the privacy. So X here can take many different shapes and meanings, especially in the language models context. So it could be they are different in just one token, and this would give rise to what we call as the token level DP. What is a token? It's basically one character or word piece in a training example that we feed into a language model. It could be the whole training example itself. So this gives rise to example level DP. And this is very standard in ML pipelines and infrastructure. It's still not a perfect fit. It's still not giving us a privacy unit that has a lot of operational meaning. And so we can go from token, example, and go down that list to paragraph, document, the whole document that we use to parse into training examples and tokens that we feed into the language model. And you can see how the unit of privacy is getting bigger and bigger, and therefore we're getting stronger and stronger protections. And the one that we usually really like is user level DP, because user level DP essentially takes all the training examples that belong to a user and swaps them with another user. So now you're giving protections at the user level. You're saying if I change one user, if I remove Peter's data from the training set, the model that I've trained does not change by much. I would still see essentially the same distribution of the models. So whether Peter is included or not included does not make much of a difference in terms of training the model. And this is not only good for privacy, it's also good for robustness and also good for generalization. And that's why DP has nice generalization capabilities. But you can go even beyond that. You can go to organization level, which in some cross-silo settings of federated learning, this actually might make a lot of sense when you talk about organizational level DP. All right, so please feel free to stop me. This is actually extremely important stuff, the units of privacy, especially in the context of language models. All right, so now that we've accepted that we want to train these models with differential privacy, one question that comes to mind is how well can we do with DP? So there's obviously a lot of trade-offs between accuracy and privacy because we're going to add randomness into the computations that we're performing, and therefore we're going to lose something. We're going to lose accuracy often. And rather than looking at it as a trade-off between accuracy and privacy, one thing that I would like to emphasize here is that we could introduce two new dimensions to the problem that helps us improve the trade-offs between privacy and accuracy. These are computational cost and data set size. It turns out that the larger the data set is, the better the privacy accuracy trade-offs. This is kind of intuitive because, if I'm training a model on one user, obviously if I take out that user, I expect the model to change drastically. But if I'm training the model on thousands or millions of users, I don't really expect the model to change much if I take out one user. Otherwise, the algorithm that I'm using would be strictly overfitting to every individual user, and that's not good, right? So data set size is easy to see. The larger the data set, the easier it should be for us to actually enforce DP without paying a steep privacy cost or accuracy cost. The computational one is an interesting one. It actually ties to the size of the batch that we're using. And even if you take one data set, say a data set of 1 million users or 10 million users, if you can afford paying a price in computations by increasing the batch size from 1,000 to 10,000 to 100,000, say, it turns out that you can improve the price of privacy in terms of accuracy, because it allows you to average updates in every round across more and more users, and that actually helps you reduce the effect of the noise. So the bottom line, and really the punchline of this slide, is that rather than only think about it as, what is the privacy accuracy trade-off, you should factor in things like, can I compute more by increasing the batch size and get better privacy trade-offs? Can I actually throw in a larger data set, collect more data, or do something? Because that is going to make it easier for me to actually apply DP. And this is interesting and important. And I also wanted to highlight it from a practical sense. All right, so we talked about federated averaging. This is the algorithm that underpins practically all variations for federated optimization. And one question that maybe comes to mind is, how do we add DP to this algorithm in this context? And one way to add DP here is to do the following. First, we would clip the updates that are computed locally on device. So this is basically a way to limit the user's contribution, to bound the influence or sensitivity any user can have on the model. And then we aggregate with a limited weight that's given to each client. Usually we do uniform weights when we train with DP, unlike without DP, where we give each user a weight that's proportional to their training examples. So we now limit the weight so that we can control the sensitivity of the query. And finally, once we aggregate those averaged limited weight clipped updates, we add Gaussian noise to actually ensure that the model update did not overfit to any particular user. So we are actually randomizing that step a little bit. So you can see 3 steps are needed to transform federated averaging into a differentially private version. And those 3 steps are all very easy: clipping, limiting weight, and adding noise. Very easy. Now, while this is actually quite easy, as always, the devil is in the details. So one devil is in terms of, are we really clipping? You really need to clip, otherwise you're not satisfying DP. Are we truly adding cryptographically secure Gaussian noise, or are we using a seed that somehow the adversary can discover and reverse engineer and remove the noise from the process? So we need to be really carefully adding a clean Gaussian noise distribution to the data. Another devil is in the analysis of privacy that we're getting. Now that we know how to actually add DP into our training procedure, how do we analyze the epsilon and delta that we get, which dictate how private we are in some sense? And this is actually quite complex. And one thing that we often do in the analysis is we assume that the users are selected essentially uniformly at random. They're selected with this, with probability Q, you sample a user. And I don't want to go into the technical details of why this is actually important or necessary. I want to give you intuition as to why this helps with the analysis in terms of strengthening the privacy guarantees. If the adversary knows the selection of the clients precisely in every training round, it can reduce the scope of the data set from, say, 100 million users to 10,000 users. Say, in every round, I have only 10,000 users. So the adversary knows in every round which 10,000 users have participated. And now it's only trying to figure out something about those 10,000 users. So it's like you've lost the size of the data set, essentially. You've lost the fact that, oh, I've had 100 million users. Now you're having to deal with 10,000 users. One way to work around this is to say, I'm going to randomly sample a batch of users in every round, and I'm not going to reveal that to the adversary. So I'm not going to tell the adversary which 10,000 users I've sampled, and I'm going to do this in a random fashion. And this is what I'm showing on this slide. This is basically each user participates with a probability Q in every round of the algorithm. And this ends up boosting the privacy because now the adversary is like, okay, I know it's 10,000 users, but I don't know which 10,000 users. It could be basically any 10,000 users. There's randomness in that selection process. And that boosts the privacy. It gives really a good boost in the privacy. In fact, let me show you this simple experiment on a language data set. So this is a language model trained on Stack Overflow posts. We're using LSTMs, so these are not transformer models. They're much smaller. This is probably a 5 million parameter model, nothing close to the 5 billion or 50 billion or 100 billion parameters that people use today. So much smaller models. And in this data set, we have only about 342,000 users. But what I want you to see is if we use differential privacy with federated averaging at the user level, without this sampling step, then we get the curve that is shown here at the bottom. This is the solid curve. This is without the sampling. And notice that if we introduce the sampling, random sampling step, we get the curve that's above it. So you can see that we can achieve better accuracy privacy trade-offs. This is the user level epsilon axis here on the x-axis. And we can go, all the way between single to double digit epsilons. And you can see that the accuracy is much better, especially at lower epsilons and in the vicinity of 4, 2, and 6, compared to the one without this step. So this is crucial. This is important. And that's why a lot of people use it all the time when they train with DP. Now, there's an issue, especially in cross-device federated learning, because these phones and computers are not always available. They can be offline. They can be, somebody is basically using their device and therefore it cannot be used for training. They may not have data. They may not be ready. They can lose connectivity, so on and so forth. So many things can happen that they could just basically go offline or come online. There's no way for the server to really track at any point in time in this large population of devices, of hundreds of millions, if not billions of devices, who's online and who's offline, and to do this sampling process from them. It's challenging on the systems level. It's also not good for privacy because we don't want the server to keep track of everybody and who's there, who's not there, and where, so on and so forth. The way it works is that whoever is online would actually submit a ping to the server rather than the server selecting them. So doing the sampling step is actually quite challenging in practice for federated averaging or for federated learning more generally. And one way to circumvent this issue is a work that we've done recently and we've since improved upon. So there's a sequence of papers in this line of work, is to present what's called follow the regularized leader algorithm, so DP-FTRL. And this one really gives you provable and formal state-of-the-art DP guarantees without requiring any sampling or shuffling of the client. So you don't need to introduce any randomness into how the clients are selected from one round to the other in the algorithm. And that's the beauty of it. Let me give you a quick preview of how this is done. So the way it's actually done is that first we ensure that the client only participates K times during the training process. And this K is controlled. It could be once, it could be twice, it could be 5 times, 10 times, but we can control it. And the way we control it is we say, okay, no client can participate more than once every 24 hours, for instance. And that's actually quite interesting. So we still clip the model update, We ensure that when a user shows up, it shows up once every 24 hours, so that if we train over the course of 5 days, the user cannot participate more than 5 times, because at most it participates once every 24 hours. Now, the other thing, which is extremely useful, is instead of adding this one-shot Gaussian noise independent from one round to the other, we add correlated stateful noise. And this turns out to be crucial to the process. And we use this tree structure that turns out to be strictly suboptimal. In a follow-up work, we actually generalized it. But even the tree structure gives a lot of gains. Now, you might be wondering, why am I adding this colored or stateful noise, using that tree structure? It's actually known as the tree aggregation protocol in the classical DP literature. And it turns out because what we care about, if you unroll the training update of any optimization algorithm, the basis of it is mini-batch DP-SGD, if you want, or mini-batch SGD. You'll notice that what you end up seeing essentially when you unroll these equations, you have all the partial sums of these gradient updates. So in round 1, you essentially have the mini batch estimate gradient G1. In round 2, you will see the learning rate multiplying G1 plus G2. In round 3, it would be G1 plus G2 plus G3, so on and so forth. So what we're actually trying to do when you unroll the mini batch gradient descent update equation, we're technically trying to actually get a sequence of increasing prefix sums of these mini batch gradients. And it turns out that this is a well-studied problem in the DP literature of how to do it. And you can give state-of-the-art DP guarantees without assuming any shuffling or sampling. So let me show you on the same data set, same model, same privacy levels, what we end up getting with this approach. And what I want you to observe is that for epsilons that are above 3-ish, the accuracy that we get from this approach, which is called DP-FTRL, is actually even higher than what we get from the amplified version, which is the one that uses sampling. So we can get really a big boost in the accuracy for the same privacy levels. Now, obviously, you can see that at very small epsilons, the trade-off is still not as great. And we've since improved the performance even in that small epsilon regime, and even in the regime where epsilon is less than 2. And so this is something that I really want to emphasize, which is it turns out that viewing the problem as one where you need to estimate a running prefix sum of the per round mini batch gradients and viewing it as a continual observation problem, bringing in tools from the DP literature for continual observation ended up helping with this problem of not being able to do sampling or shuffling of clients. This actually led to training the first model that we are aware of in production in a federated fashion with DP. This one had only 1.3 million parameters. It's a recursive neural network, so some sort of LSTM. It's used for Gboard, Spanish language, next word prediction model. The training ran over 6 days. We did about 2,000 rounds of training. And every round, we had about 6,500 devices participating. And no device participated more than once every 24 hours. And at the end of the day, the model that we obtained had a formal DP guarantee, and I'll tell you about the parameters in a bit. And the model quality was actually better than the prior state-of-the-art that was deployed in production. So this was discussed in a blog post that we shared last year, about a year ago. And I invite you to look at the blog post if you want to learn more about it. What I do want to emphasize is that we're advocating for transparency. This is the second privacy principle. So let me tell you a bit more about this. First of all, the code is online. It's available. So you can go inspect it. You can make sure that everything was implemented correctly. We truly added noise. The analysis of DP the way we ran DP, so on and so forth, everything is online. So for inspectability and full transparency, everything is out there. Second, the DP guarantee is, you can view it in two different ways. The way that we've presented in this talk is one where we tell you what the epsilons and deltas are. For the epsilons, we're talking about 8.9 for the epsilon, and the delta is 10 to the negative 10. So I think pretty good, single digit epsilon. And in terms of the trust model, we assume that the users trust the server in adding the noise. So the server is trusted in terms of adding noise, but clipping and bounding the number of participations is actually done on device. So ensuring that every device participates no more than once every 24 hours, that's actually done on device. And you clip the model update on device, but you add that stateful noise on the tree on the server. And the unit of privacy here is with respect to a device, essentially. So it's device level or user level DP with respect to zeroing out the training data of any particular user. So this is for full transparency. All right, so now that we've seen that, you might actually wonder, what if I start combining different privacy principles? So what if I take the second privacy principle, which is the one about data minimization, and I combine it with data anonymization? And already we've done something like that. DP-FedAvg is already combining these two, because federated learning is a way to minimize data. So it's a way to encode the second privacy principle, and differential privacy is a way to encode data anonymization, which is the third privacy principle. So what we have just seen already does that, but let's see if we can take it to the next level. And so this is what I'm trying to say here. What if we can clip those model updates and then discretize them to represent them in a finite group, integer modulo arithmetic, and then we can use secure aggregation to compute the sum of the model updates. Now the server can only see the sum of the clipped updates. So it cannot see the individual clipped updates anymore. It just obtains the sum of the clipped updates. And it could add the noise on top of it. So this is one step in terms of better combining DP and data minimization, because we're now using secure aggregation to ensure that the server only sees the sum. So that's great. But notice that I'm still adding the noise on the server. So I'm trusting that the server is going to add that noise. Can I take it one step further? And it turns out that yes, you can actually discretize, add integer noise, and then use secure aggregation. And now the server can only see a differentially private sum. And this is what we call distributed differential privacy, because we've distributed the addition of the noise to the clients. And for short, I'm going to refer to it as DDP, for distributed DP. And notice that now we've relaxed a lot of the trust that we were placing in the server. Namely, we're not trusting the server in actually seeing any individual clipped updates. We're not trusting the server in terms of adding noise. It only sees a noisy clipped sum of updates thanks to secure aggregation and this distributed noise process. Again, it's beautiful as a concept. The devil is in the details, so you have to figure out how to do this so that you really preserve the quality of the signal and you can give formal privacy guarantees. So there's lots of challenges, and I'm listing them in this red box here, from the fact that secure aggregation only operates on a finite group. So all these operations are now integer. We can't talk about adding continuous Gaussian noise anymore. We need to have a communication efficient algorithm. We need to ensure that the analysis is end-to-end tight, and we can get the best state-of-the-art guarantees. So let me give you a brief overview. This is developed in a sequence of papers. You can find them on the bottom of the slide and check them out if you are interested. But what we end up doing on device is we clip, and then we apply a random rotation. This is because we want to go from an L2 geometry. Clipping is basically a projection on the L2 ball. When you clip the L2 norm of a model update, you're just doing a projection on an L2 ball. but we want to go from an L2 geometry to an L infinity geometry, because when we discretize, we basically are discretizing every parameter of the model separately. And so we're really doing an L infinity type operation. We need to know the range of every parameter. And in theory, the tool that we use to go from L2 geometries to L infinity geometries is one where we do a random uniform rotation. That's one approach. You can use Hadamard matrices, randomized Hadamard matrices, or randomized Fourier matrices to go from L2 to L infinity geometries. But now that we are in L infinity geometry, we can discretize. And the way we discretize is we try to scale up to preserve precision as much as possible. And then we do randomized rounding to the nearest integer. Now that we are in integers after the discretization step, we have to add integer noise. So now we cannot add Gaussian noise anymore because we are operating over integers. And I'll tell you which noise distributions you add. But once you've added integer noise, now you're ready to do the cryptographic secure aggregation steps. So you use integer modulo secret sharing algorithm. This is the same secure aggregation protocol we discussed. And on the server, you just remove that scaling and you undo that rotation to get that differentially private sum of these clipped updates. So what are the types of noise you can use? It turns out you can use either a distributed version of the discrete Gaussian, there's a reference for it, but there's basically a discrete version of the Gaussian, and there is what's known as the scalar distribution, which is the difference between two independent Poisson random variables. And there's a multidimensional version for each one of them, whether for the discrete Gaussian or for the scalar mechanism, there is a multidimensional version for both distributions. Now, I'm not going to go into the details, but it's pretty challenging to analyze the privacy guarantee of sums of multidimensional versions of these two distributions. But this is precisely what we were able to do in our papers, because you have to really prove what happens if I sum these things, and how can I analyze tightly the DP guarantee. But what I will show you is the performance. It turns out that, again, this is the same experiment, Stack Overflow. It turns out that if we allow for about 16 bits per parameter, we can achieve good privacy accuracy trade-offs. And what is good? Basically, we can match the training that we get with centralized DP, with DP added via continuous Gaussian noise on the server. And that's pretty good. So the outcome, the TLDR here, is that with only about 16 bits per parameter, using this pipeline, this approach that I described, we can get exactly the same privacy accuracy trade-offs as if we had trusted the server to add the noise on our behalf. Again, the code is all available online. I'm showing you a link below if you wanted to look at the repository that implements this distributed DP. And just last month, or actually earlier this month, we put out a blog post describing how this technology was used for Android's smart text selection. So this is a model, it's not a language model. It's one where you put your thumb on the phone and it automatically tries to detect what you're trying to select, whether it's a phone number, address, so on and so forth, email, so, you know. We've trained it with DDP, and we believe that this is the first ever federated learning system that provides formal privacy guarantees to all users before it even becomes visible to an honest but curious server. So a lot of details, a lot of interesting references in the blog post. I really invite you to take a look at it, even code pointers, so on and so forth. But this is a technology that's actually running in production. All right, I wanted to close the talk by saying that we've barely scratched the surface. There's a lot of opportunities for privacy enhancing technologies in the landscape of foundation models. One of them is, we're training on web data. And in this talk, I spent so much time talking about user data. How do we combine these two sources? How do I take web data and how do I take user data, which is distributed across a large fleet of devices? And how do I train a model on the combination, on the mixture of two things? We've been making some progress on this front. We are calling it mixed federated learning. And there's so many interesting open questions, especially when you say that, hey, one of these data sets has low privacy constraints. The web data, you don't need to provide strong privacy guarantees for it. But for the other one, for the user data, you actually need to provide strong privacy guarantees. So how do you create a system that can ingest multiple data sets at multiple points, one in the cloud and one distributed across millions of devices? And each data set has different privacy constraints. And how do I form an algorithm that trains on the collection of these things and gives different privacy guarantees? I'm very excited about this front. The second one is about empirical privacy testing. Even if you don't train with DP, or if you train with a DP epsilon of, say, 100, which is vacuous in theory, so it does not give you anything that is strong in theory, can you still try to do some privacy attacks? Can you still try to see if the model has memorized, overfitted? What can you learn? How can you empirically validate that the DP mechanism was implemented correctly? Or what is the information leakage that we're getting? So this is known as privacy auditing or as red teaming. You may have seen that term. We think there's a lot more work to be done in this space. And finally, I do think that this right to be forgotten principle that we talked about earlier in this talk is actually quite interesting. Especially in light of this foundation model, the model that violates someone's privacy using public data is going to be a bit of a problem. So how can we find a way, figure out a way to actually circumvent this issue of the right to be forgotten that GDPR presents? And with that, I'll stop and we can maybe take a few questions. Thanks a lot for listening.
Thank you, Peter. It was a very timely and interesting topic. I